Guess we'll get started. So, yeah, previously we were looking at ideal reactors, and the next module, module 9, is basically reactor design and optimization. We've already started looking at design problems, design equations, and so on. So, what I thought was, rather than spending more time on this particular module, I'll try to finish it basically in 2 lectures. So, 1 lecture plus 1 tutorial. Instead of going through everything that is there, I will cover key concepts and link it to what you already know, so that module 9 will be a little bit light in that sense. Okay, so we'll just sandbox it to one single concept, and that is how do you do the optimization, and we'll take up a couple of examples which as chemical engineers you are already familiar with. As non-chemical engineers, we will have a very quick introduction to that and wrap it up. Why? So that we can spend a little bit more time on the case studies. So fixed bed reactors and batch CSTR case studies is something that we will spend a little bit more time on. Okay. So as I said in the previous class, today we will take up Excel, okay, and look at one particular example. The example that we will look at is, instead of, so last time what we did, I forgot to change the title of the. So last time what we talked about is we want to do this non-isothermal PFR. Okay, so this non-isothermal PFR, it's a little bit straightforward. If you read all of the material, you will easily be able to manage. It's just a matter of substitution of all of those parameters in what we have discussed in the previous lecture. It's just a matter of substitution. There's nothing majorly new concept in that. If you are still confused, if you still need help, reach out to TAs. They can schedule an additional session, help session for you. Okay, but essentially whatever you need in order to solve this particular problem, you already have. And as I had said in the previous class, that your assignment problem is no different from this, other than the fact that parameters are different. Okay, the activation energy is lower, the pre-exponential factor is lower. So this is an example from a highly reactive system. The other one is an example from a less reactive system. So that's the only difference, but otherwise there is no difference. What we will do instead today is solve a problem that is of a similar nature, but a bit more complex. Okay, what I mean by that is, if you look at these equations, the equations that we have, or reactions, not the equation. The equations remain the same. The reactions that we have are of the nature of okay, where A is ethane, oxygen. So this is the example that we will take. Okay, why? No reason. It's just that we will solve using Excel. So we'll take up an example that has a direct research/industrial significance. The only thing that is correct about this is the form of this equation. Okay, the thermodynamics form is actually correct. equilibrium constant is not 5. Equilibrium constant has a temperature dependence, right? A to the power minus delta G by RT. Delta G is dependent on temperature. Therefore, K equilibrium, which is also dependent directly on temperature through the exponential term, is also temperature dependent. We have not considered that. The equilibrium constant is not 5. Equilibrium constant, actually one of the problems with this reaction, its equilibrium constant is actually quite low. The other thing we have done is this, it's a Langmuir-Hinshelwood type of a term. Instead of bringing in that complication of Langmuir-Hinshelwood term, I have just simplified it. Okay. So later on, don't come and ask me that, oh, you have not taken up an actual case study. This is an actual case study. We have just simplified it so that we can solve it in a class. Okay. This is a significant challenge in the industry. Okay, this is something that people have been working on for more than 30-35 years. Okay, this is an example of oxidative dehydrogenation. The problem with this reaction is that the side reaction, or actually I made a mistake. Sorry, this is how it is. Okay, so this particular species, or maybe I'll write it. Okay. So, one of the interesting things is that the rate constant for this reaction is lower, but so also is the activation barrier. And if you increase the temperature, what happens is that the reaction proceeds too much towards A going to B going to C, right. So, it proceeds too much towards C or too much towards D. If you go at a lower temperature, the problem is that there is not enough reaction. So, it's a very tough problem, and people are trying to solve by finding different catalysts for this type of system. So, this particular mechanism is for vanadium type of a catalyst. Again, this term is actually a Langmuir-Hinshelwood term. It is not a power law term, it is a Langmuir-Hinshelwood term. I have just arbitrarily replaced it with a power law term, just to make things not very complex. Okay. These numbers again are not exactly correct, but what is correct is basically we use ethylene to oxygen in the ratio of 1:half. Okay. And oxygen to nitrogen is in the ratio of 21:79. Why it is 21:79? Atmosphere approximately. Okay. So, this is carried out in air rather than in oxygen. Okay. So, that is the background. So, you know, other than the fact that there are a few simplifications here and there so that we can solve it in class, there are no other simplifications over here. Okay. What I want to show is basically you know, how we will solve this using Excel and where does the optimization aspects come into picture. Okay. So, that is what I am going to try to do this with this example. In the next class, what we are going to do is we are going to take a tutorial. Okay. First few minutes or first 10 minutes, I will take time to actually show what you would have done in your undergraduate for A to B to C in a batch reactor. Again, in your undergraduate, you would have also done A to B to C in a CSTR, but doing that in a CSTR will be your tutorial problem. Okay. So, that is what we will do. Over the weekend, I will upload a few things, a few reading material for you on the website. Now, how do you go about doing this? The way you will go about doing this, okay, in module 4, sorry, module 3, we looked at the reaction A going to I going to P. Okay. Yeah, just replace these guys with B and C. We have just changed the letters, nothing else has changed, right. So, this is K1, this is K2. Okay. So, we then obtained Ca right. Blah blah blah. Okay, I don't remember, so you can just open up your module 3 and look it up. We'll do this on Monday. Okay. So, the question is, right, if you remember from the Excel sheet, I might actually have the Excel sheet. Ca falls like this, Cc goes up like this, and Cb will go like this. So, it could go like this or it could go like this, whichever way. Okay. What we want to find out is the time t at which Cb is the maximum. Okay. Okay. Remember what we did? Right. And that is the concept that you are going to use. Okay. What that means is, this particular expression that you get, this is your f as a function of t. Okay. So, to find the time at which, to find the batch time at which this is maximum, okay, and that is essentially what you are going to do. You have two ways, not two, there are multiple ways to do this, but essentially all of them are equivalent. You get your Cb expression, right. From the Cb expression, you differentiate it with time, equate it to 0, you will get T star. Alternatively, dCb by dt is what? It is K multiplied by Ca minus K1 Ca minus K2 Cb. Okay. So, the time at which Cb is maximum is the time at which Cb divided by Ca is equal to K2 by K1. Okay. If you use this, it is just algebraic manipulations. If you use the previous one, you also need to differentiate it, that is all, but you will get the exact same results. Okay. This is what we will do as a part of the tutorial for, or you will do as a part of the tutorial, not for batch but for a CSTR. Okay. Today what we are going to do is take up this particular example. Okay. Slightly different, the equations that we have are going to be okay, and we are going to solve ODEs. Okay. you can use a higher order solver. Okay, what we are going to do today, we will just use Euler's method. Okay, Euler's method is something that even in 11th and 12th probably you might have been aware of, which basically means that if you have dy by dt equal to f and you start with y naught, you will take and a step size, then y1 is just going to be y naught plus h multiplied by f of y naught. y2 is nothing but y1 plus h multiplied by f of y1, and so on. This is your Euler's method. I am not expecting you to know Euler's method. Okay, we will put this as Excel sheets, and you can play with the Excel sheets to try to understand the behavior. I am just kind of showing you how you can solve the problem. In the next semester, you will solve the problem using MATLAB. Okay. This rest of today's lecture is just to give you an idea of how we can use numerical techniques in order to solve fairly complex problems using the tools, using the concepts that you already know. The tool is something, this tool is something that you will learn next semester if you do the MATLAB course. Today we are only going to show how we will solve this problem. For your assignment and for your exam, what I am going to do today is not relevant. Okay, this is just so that you can see the power of the things that you have already learned. Okay, I would, however, request you to play with the Excel sheets that we will upload. Okay, in 2022, actually I was just looking back at my notes, in 2022 and in 2018, we had actually done 4 or 5 examples. I don't know why, how we found time to do that many examples, I don't know, but we had done 4 or 5 examples at that time. So I will try to upload the Excel sheets from that time as well. Okay, this is basically for your enhanced learning. The intent of today's class with respect to the course, we aren't worried about grades and all that, right? Fair enough. Intent of this class from the perspective of this course is really for you to understand PFR, solving PFR equations, for you to understand where does the optimization problem comes in. Okay, the tools that we will use today, we are not going to use it either for assignment or for your quiz. Okay. Okay, so what do we have in this case? We have a constant volume batch reactor. So constant volume batch reactor, so not these equations, but constant volume batch reactor equations are which will give us its constant volume. So it's dCk by dt equal to Rk, right? Concentration of ethane. So what are the species? Species are E, O2, Ey, H2O, CO2. E, O2, ethylene, H2O, CO2 and N2. this is time. Okay, we'll start with 0, 0.01, or let's have step size over here. Okay, so this guy is going to be equal to this plus step size. Okay, we are just setting things up. Concentration in the beginning 5 moles per meter cube, 2.5, 9.4, 5, 2.5, 0, 0, 0, 9.4. Okay. We have our K1. Let's calculate reaction rate R1 and reaction rate R2. R1 is 0.15 is equal to 0.15 multiplied by concentration of ethane to the power 0.75 into concentration of oxygen. Yeah. You can see all of this or no? No? Now? I can't. Okay. What we did. Let's see. I'm not used to Windows anymore, so I struggle a bit with that. Okay, let's paste this here. Okay, so reaction rate is 0.15 multiplied by concentration of ethane to the power 0.75. We can't see this. Okay, concentration of ethane, this is here, to the power 0.75 multiplied by concentration of oxygen, that multiplied by 1 minus, what do we have, ethylene into water, 1 minus ethylene into water divided by 5 into ethane into oxygen to the power 0.5. Okay. Okay, so this is the reaction rate for the first reaction. Okay, again, if you look at the format of this reaction, right, a reaction rate, it's forward reaction rate multiplied by 1 minus product of concentrations to the power of their stoichiometric coefficients divided by Kp or Kc in this case. Okay. What about the other guy, the other guy is 0.06 multiplied by concentration of ethylene multiplied by concentration of O2. So that's 0. Okay. So this we are done. I will maybe we'll need just keep it over here. Why will I need it? I'll need it for stoichiometric coefficients, stoichiometric numbers. Okay. Let's then look at the rate. So, of formation of species, right. So, what do we have? We have the equation as dCk by dt equal to Rk. What is the rate of formation of E? See, E. Rate of formation of E is nothing but minus 1 multiplied by R1 plus 0 multiplied by R2. Okay. So, I will just say okay, this is just to show you how to do. Okay. So, stoichiometry, stoichiometry of reaction 2, stoichiometry of 1 is minus 1, minus 0 0.5, 1, 1, 0, 0. Stoichiometry of 2 is 0, minus 3, minus 1, 2, 2, 0. Yeah. With me? These people are nodding, so I don't realize if others are. If you are not with me, just raise your hand. Okay, we'll go over it once again. Okay. What I am trying to show you is basically this follows a very clear pattern, a very simple algorithm, and you just do it carefully, and you will be able to solve fairly complex problems as well. Okay. Okay. Rk is what? Any rate capital R okay. So, this is, if you think about the Excel sheet, okay, this is where right. So, this guy over here is nothing but nu k1 R1 plus nu k2 multiplied by R2, which means it is this guy, multiplied by this guy plus this guy multiplied by this guy. This is what your rate is. Okay. What does that imply? This is going to be equal to this multiplied by this plus this multiplied by this. We will put dollars. Thank you. Very nice. Okay. Now, we are going to drag them down. When you drag them down, your 2 and 3 should not change over here, right. So, when you are dragging them down, your 2 and 3 should not change. We will put dollars over here. Okay. When you go from 5 to 6, 6 to 7 and so on, your 5, 6, 7, 8 should change. Okay. Now, when you are dragging them in this direction, okay, your your H and I should not change. So, we will put this dollars. Okay. And again, if you didn't get this, that is perfectly okay. We will just move this over here, right. Let us see what this is. This is this blue multiplied by red plus purple multiplied by green. Okay. You've not done a lot of Excel, then don't worry about where to put the dollars. That's perfectly fine. All you want to do is check whether or not these numbers are okay. F2, this multiplied by this plus this multiplied by this. Okay. Now, just look at this value, right. This is nothing but this rate of reaction with a negative sign. Why? Stoichiometric coefficient is -1. This is nothing but half of this rate of reaction with a negative sign. This guy is nothing but equal to this rate of reaction, but with a positive sign, equal to this rate of reaction to positive sign. Okay. So, this is the reaction rate R. Okay. Now, if we look at our Euler's method, your Ck at the next time step is Ck at the previous time step plus step size multiplied by f. Okay. We will write that like that. Okay. So, this is nothing but equal to Ck at the previous time step plus step size, which is this multiplied by, I will right now just put 0 over there. Okay, I have to put something, I will replace that 0 with something. Okay, this is what this is. Okay, now when we move up and down, your H value should not change. Sorry. Okay, so I will put dollars over here. Okay, over here, when you drag this down, your 5 should change to 6, 6 to change to 7, 7 to change to 8, but when you drag left, your B's should not change. Okay, so I will put the dollar over here. Okay, if we do that, let us see what happens. Oops, some mistake. Oh, there should not be a dollar at here also. Yeah. Okay. Now, what is our f of x? Our f of x is nothing but Rk. Okay. What do we mean by that? That 0 that we put over here, this 0 has to be replaced by this guy. Okay. So, what will I do? Just take this, Control C, go over here, replace that 0, Control V. Okay, and then drag. Okay. So, let us look at this. This is nothing but previous value of this plus h multiplied by this. There is a problem, I did not put brackets, put the brackets over here. Okay. Okay, so this is what you get. Okay. then this rate of reaction, just drag them. Okay, check. Okay, okay, 0.15 multiplied by Ce to the power 0.75 multiplied by CO2 to the power 1, the whole thing multiplied by 1 minus this concentration into this concentration, purple into green divided by 5 multiplied by this concentration multiplied by this concentration to the power half, 5 multiplied by blue multiplied by red to the power half. Okay, so that just to confirm that our rate of reaction is also fine. Okay, we will go over here, take this, go to this end, double click. This is how our concentrations of ethane, ethylene and so on will change with time. Okay. Actually what I will do is I will also make one more check. I will just go to what happened? Okay. I will just go to any one of these guys, let us say over here, and do an F2. Okay. So this value is this blue value multiplied by what is red, red should okay, where what do we have? We have Ck is Ck from the previous row plus H multiplied by reaction rate. Okay. So Ck in the new row is Ck in the previous row, that is the blue guy, plus H is our red H. Let me scroll up. Yes, our red okay, our red is H multiplied by mu 1 R1 mu 2 R2. Okay. So let us see R1 and R2 what they are, green and brown, green and brown. Okay. Now we want mu 1 and mu 2. Okay. So it should be in the same row, mu 1 mu 2, right, sorry, same column, mu 1 and mu 2. Okay. So we are looking at purple and violet color or violet and purple color. Okay, I will just scroll up. D, I am pointing at D over here for myself, you will not be able to see where my finger is. Okay, and I am scrolling up. Okay, purple and violet. Okay, so that is what. So just to verify this. Okay, so let me zoom out a bit. Okay. After 8 minutes, looks like the first reaction has reached some kind of an equilibrium. Second reaction is still perhaps going on. You can keep dragging. Okay. So let us say we wanted to find how ethylene changes with time. insert charts scatter plot. Okay, this is how ethylene changes with time. Okay, it has a maximum somewhere around 5 hour or 5 minute, I don't know, that mark. Okay. The other thing that you will notice is the total concentration, and therefore C by RT will be total pressure is going to change with time. What's going to happen? It's going to increase with time, right? Why does the pressure increase? More number of moles formed compared to moles that you started off with. Okay. So yeah, that's what we have for today. Okay. So this is a semi-real example. What's the date today? 24th. Okay. So, and if we were to plot the yield of ethylene, we will get, not a very high yield. We started, remember we started off with 5 moles, okay, and the max amount of ethylene that you are getting is less than 2, right. So, about 40% yield, okay, which is the challenge with this reaction. Okay, the challenge with oxidative dehydrogenation reaction is that the subsequent reaction, which is ethylene getting completely oxidized, is an easier reaction than ethane getting oxidized to ethylene. Okay, this is what causes a limitation on the utility of this reaction as of today. So, what we do in the lab is basically try to get catalysts which are either more active or more selective. Okay. If we get a very active catalyst, then we can use our engineering principles to stop the reaction, not stop, but have smaller reactors to stop the reaction at the optimal time. If we have a more what do you call more selective catalyst, that means the rate constants are going to be smaller. Let me show what I mean. You are confused, right? But so far this was okay. Okay. Chemistry, folks. Who is chemistry? Okay, or confused? Completely confused or somewhat confused? Yeah, you are free to leave. I'll just show you something. Okay. So let's say we have a more reactive catalyst. Okay. What does more reactive mean? Instead of 0.15, this will be say 0.3. Instead of 0.06, it will be 0.12. Okay. Both the rate of reactions have increased, but by the same amount. The ratio is not remain the same. So let's try and see what this will do. Okay. So 0.3 over here and 0.12 over here. Okay. I'll just double click this. Okay, I'll just double click this. Okay. So what happens? you see that the maximum has shifted towards an earlier time. Why? Because everything is speeding up. Okay, both the rates of reactions have gone up. Okay, so you will want to stop it at an earlier time. Okay, let us say instead your selectivity has increased. How can your selectivity increase? The next rate of reaction, let us say, has reduced. Okay, so your maximum that you can get increased. Okay, slight shift, but not much shift in the maxima. Okay, on the other hand, you can have this because this rate of reaction has increased. So this has become 3. Okay, the maximum value has a similar effect. It goes slightly above 2, but the time at which it goes has also shifted. Okay, so you do have an interplay between when the optimization happens and how much ethylene you are going to get. Okay, so when we actually do experiments and design catalysts, the way I could change K1 and K2 the way I wanted, that's not in my hand. Okay, it depends on the catalyst itself. So you can change the catalyst, K1 and K2 both change in some way or form. Okay, what we try to do, for example, with AI tools, machine learning tools, is we have a whole bunch of database that based on prior experiments that people have already developed. Okay, so we try to see mixtures of the catalyst. So you take this component, mix this and so on, and try to see how those mixtures can change your K1 and K2. Okay, do they actually change exactly in that way? No. Okay, but we are trying to use tools like machine learning in order to be a bit more predictable. So you won't necessarily get it exactly, but qualitatively you will be able to get it in the right direction. So lot of catalysts today will have 5 or 6 different components included in it. Okay, so that you push K1 a little bit in this direction, K2 a little bit in this direction, you add some components so that K1 and K2 increase or decrease depending on case might be. So that we are trying to shape this curve that you see, okay, such that we can get as much ethylene as possible. Okay. So, and if the question is what is the concentration of ethylene or what is the maximum concentration of ethylene, your answer is something which you see over here. If your question is what is the maximum selectivity of ethylene, right? So, what is the selectivity defined as? Selectivity will be defined as the concentration of ethylene divided by concentration of CO2, or concentration of ethylene divided by ethylene plus CO2. Okay. So, this is going to be equal to ethylene divided by so in fact it won't be defined like this, it will be defined in terms of carbon selectivity. So it is 2 multiplied by ethylene divided by 2 multiplied by ethylene in the denominator and 1 multiplied by CO2 in the denominator. Why? CO2 has 1 carbon, ethylene has 2 carbons. Okay. So, if If you look at the selectivity, selectivity keeps going down, okay, and it stabilizes at some point. Okay. So, when we talk about a maximum, now what is the maximum selectivity over here? If we were to use d by dt type of a concept, we won't get any answer. Why? Is because there is no maximum minimum happening at all. Okay. So, it is not about using the tools blindly also, it is also about what is the question that you are trying to probe. Okay. So, there is no reason to necessarily say that in a problem like this maximize the concentration of A or B or C or D. It could be maximize concentration, maximize selectivity, maximize yield, minimize the waste, minimize energy input into the system, any of those cases. Okay. What you want to optimize on goes in the numerator, what is the handle that you have goes in the denominator in df by dx. Okay. All right. Yeah. So, that is what we have for today, and I will see you on Monday. Okay. Just to recap what we did today for the last 35 minutes was really to give you a flavor into how the concepts that we have learnt over the last 11 weeks are directly applicable in industrially or research relevant problems. Okay, that was the aim of today's exercise. Okay, and just to introduce you to the fact that when we talk about minimization and maximization, there is a trade-off, and that trade-off depends on the questions that you ask.